So let's go. Why are we here? Well, we have won the Semantic Textual Similarity task within the SemEval 2016 contest. This contest dates back to late 1990s, so it has got a lot of traditions. The task that we have participated in was about recognizing paraphrases. So you would have to input sentences and you would have to assess how similar in semantic terms they are. Well, the previous meetings of PyData Warsaw were focused mostly on processing images. We would like to join in and to extend the meetings with some textual analysis. So why is paraphrase detection important? There are many industrial applications. One of them is question answering. You can imagine that you have a large database of FAQ questions, and you have a new question from a user, and you would like to match the new question with your database of the known questions. The other one may be plagiarism detection, where you have some texts and you would like to compare them to make sure that the author of the text is really the author. Some other case can be information retrieval or machine translation and many more. Why is NLP and paraphrase detection hard? Well, language is ambiguous. First of all, we have to deal with syntactic ambiguity. There is a sentence in here. You can play with it and try to interpret it in more than one way. It's quite easy, I think. Words are polysemous, which means that a single word may mean many things, like mouse. It can be an animal or a computer device. A single sentence can be very long and very complicated and thus hard to parse. And if it is hard to parse, you can make some mistakes at the beginning of your process, which means that the error will propagate. We usually don't deal with single sentences. We deal with many sentences, and we have to know how to split the paragraphs into sentences. So we have to be able to detect the boundaries. Here, for example, you can consider this dot and this dot. Do they end the sentence, or are they the part of the sentence? There are named entities like Washington. We have to know whether this means the place or a person or something totally different. The same may refer to the word may. It may be a month or a person, like Prime Minister of Great Britain. Also, the context is very important. When you say how far is it, you have to know whether we are considering miles or kilometers. Social context is also very important. When you say that was bad to your kid, it means that you are reprimanding the kid. And when you say that was bad to your friend, it may mean appreciation. There are spelling mistakes in the text. Here you have some spelling mistakes for word galaxy, and these spelling mistakes actually come from word embeddings. We will speak more about these later on. You have to deal with slang, with jargon, and with abbreviations. Here is the actual question that we got from the user. So our customers expect that we will be able to answer such questions. As you can see, the task is not that easy. Most of these issues, and these aren't all of the issues, come up somehow in detecting paraphrases. So we need to find some remedies. When you work with images, you usually work with rich and high-dimensional data. The data is encoded as a vector. and it's very nice as a computational unit. In language processing in the traditional systems, we usually work with sparse data. It means that we have very long vectors, as long as your vocabulary is, which means as many words you know, and this vector is mostly zeros, and it may only contain some numbers which will refer to the frequencies of these words. These vectors are not very good to work with. We need something more, and word embeddings provide us with some kind of solution. What do word embeddings do? These are actually the vectors of real valued numbers, and they represent words in a continuous vector space, which means that the words have some relations which you are able to track these relations in the vector space. So, for example, if we have a word vector for word king, we can extract the word vector man from it. Then we can add the word vector woman, and we will one of the closest words to this combination will be the word queen. So, king minus man plus woman equals queen. These vector spaces may also contain other information, like some grammatical relations between words. The most popular models to train are Word2Vec and Globe. This one comes from Google, and this one comes from Stanford University. We are on PyData meeting, so let's show some code in Python. What we are doing in here, we are using the Gensim package. It is publicly available. We are loading, it is an interactive session. We are loading a Word2Vec model. We are loading the data, the word vectors. You can download both the package and the data. It's publicly available. And here we can check how does the vector for the word vehicle look like. So we have some values, first 10 values of that vector. These are just numbers, it's very hard to read actually, but what we can do, we can use these values and count things like cosine similarity. So if we check the similarity for words vehicle and car, we get a very high score. The maximum value in here is 1. So we can assume that words vehicle and car are very similar. So this is one part. We have some way to represent the words in a more complicated way, but we don't work with words. We are working with sentences, and we need some way to aggregate the data from words. And to do so, we can use autoencoders. This is a very simple kind of, it doesn't have to be simple actually, kind of neural network. And when you say neural network and very simple, that's a strange thing to connect, I guess. But the autoencoders themselves are unsupervised or actually self-supervised method, which means that the input and the output are the same values. So when you have 2 at the input, you encode it to some representation, and you should be able to more or less decode it and get the input value. I will try to show you some simple example. On the left hand side you have 8 vectors, 8 one-hot vectors of length 8, so there's one vector, the second vector, and so on. And we would like to encode them, which means that we would like to find some kind of representation that will hold this information, but in a more compressed way. If you have some background in computer science, you will quickly recognize that you can show this data as a binary representation. So you can encode all of this information in a vector of length 3. And once you have it, this is the thing that you would like to learn, you can use it to decode your original information. Once again, let's go to some code. This code was written in TensorFlow, so we are using TensorFlow in here. I will just get through it very quickly, but it is like 25 lines of code, which means that in 25 lines of Python code you are able to build your autoencoder and to perform the thing that I have shown on the previous slide. So here we are defining our input variable. This is a neural network, so we need some hidden layer. Here's the definition. We need some output layer, which will hold the decoded values. Then we need to perform some classical computations. We are counting the values of the hidden layer, and we are counting the values of the output layer. Finally, we need to define some error value, some loss function. In here, it is mean squared error, and we also need to optimize the error. And this is how the definition of the network look like. Then we need to train our network. To do so, we have a variable called I. It holds the vectors which are one hat, which means that they have only one value which equals 1, and the rest of the values are equal to 0. This code actually trains the network. So in here we are running this operator. It was defined on the previous slide, and we are training the network right now. When it is done, we are using 50,000 iterations in here, but it takes about 2 minutes to train that kind of network, so it goes very fast. When this is done, we are able to encode our information. So here we have some input data, and here is what our network will be able to return. So as you can see, we have learned exactly the binary representation for these 8 vectors. Once we have the learned representation, we can use it to decode the information and get it back. So these 3 lines of Python code are able to, given this input, return this value, and so on. So in here, as you can see, there's no loss of information. This is actually not the kind of usage we would like to achieve. We actually want this hidden layer to learn important features of the text, not all of the features. So when we are comparing these vectors later on, we hope that they will keep only the important features. Okay, but in real life things aren't that easy. We don't work with one-hot vectors. We are working with word embeddings, and we are working with parsed trees, which means that we have tree structure-like structures of data that we have to deal with. To do so, we use recursive autoencoders. So you can imagine a situation like this. You have this simple sentence: boys play football. You take the word embeddings. These actually represent these real valued vectors for each of these words. Then you would, given the parsed tree, you may want to encode these 2 words into a single vector. And to do so, you're trying to learn this vector so that it will be able to decode the input values, which are the same as these. Once this is done, this is the first step. we still need to do something with the word football. So we are trying to encode this information into that vector. So we are trying to learn this vector, which will hold all of this information. We do so. This is actually one of the possible strategies called the unfolding strategy, which means that given this vector and only this vector, we are trying to decode this word, the football word, then this intermediate vector, this one, and the words for boys and play. Okay, so this is the final vector that we come with, and we assume that this single vector will hold the most important information extracted from these three vectors and these three words. So these things are the building blocks of our solution. Now we can go to the SemEval contest. As I've told you before, it is an ongoing series of evaluations for various semantic analysis systems. You can think of it as an Olympiad in semantic analysis, because there are many tracks. There are 5 tracks actually, and each track holds many tasks. We have started in track 1 and task 1. So the traditional way to go with this is, first we have some input paraphrases. I mean, the organizers have it, which means that they have pairs of sentences. Then they give these pairs of sentences to linguists. They do the annotations, and once the annotations are done, this is treated as the gold standard. Then we have to create our systems, I mean the participants, and produce our outputs, which means that we are predicting how similar the sentences are. And once we have this and this, we are able to compare both and get the scores. Once this is done, it is possible to answer the most important question, namely who won. Our solution, the simple version, the basic version of our solution is like this. The question is, are two sentences similar? I actually mean, do these sentences carry the same meaning? So we can imagine that we have these two sentences, quite easy ones. Cats eat mice and fish. The cats catch mice. You may wonder how you would classify them. Are they similar or not? But we do that thing with our systems. So you know these building blocks already. Here you have words, here you have word embeddings, and here we do the auto-encoding. So this is the last vector for this sentence, and this is the last vector for this sentence. We assume that it holds the most important information gathered from the intermediate vectors. Once we have this, we are building a distance matrix which actually contains the information about each of the words, each of the intermediate vectors, and the final vectors. Here, for simplicity reasons, we are only showing the words, but you can imagine that this matrix is actually big. It's not that small. So once this is done, there is a problem with word embeddings, because in word embeddings some words that are actually opposite may land close to each other. We would like to be able to say whether a word is a synonym or an antonym, or whether the similar words like in the vector space, words like Monday and Wednesday will be close to each other, but in the sentence they may mean totally different events. That's why we need something more, and we are using WordNet. This is the linguistic database. So we are trying to somehow award some words and penalize others. This is the kind of penalty, we call it out of context penalty, which means that this word is not similar in any way to any of these words given WordNet. So once this is done, we are changing these weights somehow. Then we are making some min pooling. It's not in here on the screen. And once this is done, we are changing this matrix into a vector, a big vector with all of these numbers, well min pooled. And we are using the support vector regression to count our final result. And let's assume that in this case, the answer is 345. Are you satisfied with that answer? I guess you may not be, but in our system it's actually quite a good answer because the scale was from 0 to 5. That's how the original linguists classified the sentences. 0 means that the input sentences are not paraphrases at all, and 5 means that they are exact paraphrases. So in here we may be quite satisfied with the score. Okay, so this was our basic solution. We can go to the results now. As you can see, there were 5 data sets. Our solution was achieved best scores on 3 of these data sets, and our weighted mean for all of these data sets was highest. That's why we landed in the first place. But the thing that I have just discussed, our basic solution was actually 10th. Because in the way we have worked on some other solutions that were ensembles, which means that they were using this solution as one of the classifiers and 2 others. I won't discuss them in here because I don't think we have time for it. But we can discuss that thing later on. We are staying on the after party. Here you have some of the participants. As you can see, some companies have participated, some public research institutions, and a number of universities. So there's actually more, but we can't see it. Okay. So the total was, there's some difference because on your slide, Bartek, the number was like 43, I guess, but I have this data from the very early Excel file from the organizers, so that's why the difference. But the thing is that each participant was able to submit 3 runs. So we are happy to with the fact that all of our 3 runs made it to the top 10. This list actually goes down to like 113 rows. Okay, so that's it. If you would like to read more about this solution, you can read our paper. It's published and it's online. Or you can try one of our presentations, which was given in the Polish Academy of Sciences. It is also available online. So at the end, please let me name the core members of our team: Basia Rychalska, Kasia Pakulska, Krysia Chodorowska, Piotrek Andruszkiewicz, and myself. Thank you.
Thank you so much for your speech. We have time for 2 questions. Okay, already 2 spots.
Thanks and congratulations. So
Thank you.
Just a super quick question. The difference, accuracy was the measure, but everything was scored on, right?
That's right.
So
well, actually no. The measure was Pearson correlation R.
But anyway, so typically when we design these systems and then put them into production, there is a big equation to solve, or to make it more complex, meaning ensemble and slightly
right.
better, or much simpler and much faster and also less costly to maintain. So if you were to make a decision which one of these to put into production, which one would you choose?
I don't know if I'm able to say, because we've made the decision, and our decision was to use the basic solution. The thing is, the basic solution was actually written in Java. The ensemble was created out of 3 components. One was written in Java, one in Python, and one in Torch 7. So it would be hard to maintain all of them.
It was a technological choice.
That's right, yes. So we've actually decided to stick with our basic solution.
Thank you.
No problem. Thank you.
Okay, second question.
It's actually 2 questions. The first one would be, what is the benefit of using recursive embeddings rather than just say doing autoencoder on the entire sentence? Let's say the most words that you have in a sentence would be 20 in this data set. So why not go 20 to the embedding of those 20 vectors and then back? So if there is any benefit, and I suppose there is, in using recursive autoencoder, how do you choose which words you combine together? And because in the example that you showed, you actually had first 2 words when you encoded those together, and then it wasn't the second 2 words that were encoded together. It was rather the second one, and then the words after that were combined. And the second question is, are you familiar with any not co-occurrence-based word embeddings? Because you said there is a problem with synonyms and antonyms, and of course it comes from using the embeddings based on co-occurrence. Are you familiar with other methods? Have you guys used other methods? And
Okay. Yep. So one of the questions was why do we use recursive autoencoders, and what is the order of combining them? So actually, I think that the parse trees part, because the order may be important, because some entities are larger than one word. And when we have the parse tree, these are usually combined, so we combine them first. And this thing may be very important when we are then comparing them, because first we would like, if we have like a phrasal verb like carry out, we would like to first combine the words carry and out, and not with some other words. That's why we use parse trees, which give us some order in which we should combine the vectors. That's why we use it. And here I think that we would actually go the other way around. We will first combine the word play and football, and then we would add boys. So we do so because in language there are entities larger than one word, and we would like to combine them in the right order. It may also be important for how these words lie in the vector space. So this is I think that this actually answers 2 questions: why we use parse trees, and why we use some order, and why we use and why we combine them in this order and not the other. So we use the parse trees because they offer us the right kind of relations between words, and we don't want to use that, and don't want to lose that kind of information. And the second question.